Hello and welcome to Exponential Functions. We're going to look at things that grow at an exponential rate or decrease at an exponential rate. The form for an exponential function is y equals a times b raised to the x power. The a value is our starting value. So that's where we're beginning. If we have year 0, if we're just beginning, how much are we starting with? And then b is the rate of growth or decay. Now, if b is a number that's greater than 1, it's going up. It's a growth. If b is a number that's less than 1, it's a decay. That's one of the tricks you can use to help you. In terms of the graph, if it's growth, it's typically going to look like this. And this point here where it crosses, that's the y-intercept. That's where your a value is going to be. And b basically controls how steep is it. Is it like this or is it like this? How fast is it increasing? So here's an example where we have a bunch of points. And the thing to do here is to check to see if it's exponential. We want to see if it's a constant rate of multiplication all the time. So if I take 27 divided by 81, I'll do that on my calculator. 27 divided by 81, I get 0.33. So the 27 had to be multiplied by 0.33 to get to 81. I'll check this the same way. 9 divided by 27. 3 divided by 9. 1 divided by 3. If that's the same, then it has a constant multiplier. Okay? And so that's what tells us this is an exponential function. The b factor then is going to be this 0.33. It is decay, it is not growth, because it's getting smaller and smaller and smaller. Because this number b is less than 1, it's getting smaller and smaller and smaller. Okay, so the initial value, that's where's my starting amount. And sometimes on a table it's really easy to see. It's right here, it's wherever it's 0. So we know the starting amount for this one is going to be 81. Okay, so I can put that together. My equation will be y equals 81 is my starting amount times 0.33 raised to the x. That's how I can come up with the equation. You can pause that if you need. In the next one, I create this example because it's a little bit different. There's two things that are different about it. First of all, you see it's not going down, it's actually going up. Probably going to be growth. Okay, so we have 29 divided by 13, and I get 2.23. When I do 64 divided by 29, I get 2.2. I think the error is okay there. 2.2. Let's just use 2.2 every time. 309 divided by 141, 2.2. Okay? So you see that this is a number bigger than 1, so that tells us it's growth, right? So our b value here is going to be 2.2. This is growth. The a value here, they don't tell us. There's no 0. I would like to see, well, what about when it's 0? So the way to figure it out is you take the 13 and divide it by whatever this is. Let's go one step back. What if I took 13 and I divided it by 2.2? Is that what you were guessing? So that gives us 5.9. So the a value, the initial value, is 5.9. So my equation I can put together. We're starting with 5.9 and we're going up 2.2 as a multiplier each time, raised to the x power. Notice all of these will have the x as an exponent. That's the difference between exponentials compared to linears. Okay? On the back of your paper, you'll see there's a application problem here. Let's see if I can make this work. Come on. Suppose there are currently 950 students at Aurora High School, and the number of students is increasing exponentially by 8% per year. Now this is telling me this is going to be growth, right? Because it's increasing. The a value here is our starting amount, that is 950. Now the b amount, though, we have to be careful. It's not just 0.08. That is not correct. because that would be saying that would be decay. We know it's going up 8%. That means it's more than 100%. It's over 1 by 8%. If it's growth, it's going to be that much more than 1. If it was decay, it'd be 8% less than 1. So my B value here, we have to be careful. That's actually going to be 1.08 because it's 8% above 1. So my equation I can write y equals my initial amount times 1.08 raised to the x. I hope that makes sense to you. Or it says, how many students will there be in 5 years? Well, in this case, y represents the number of students there will be. X is number of years. In year 0, we know there's 950 students. In year 1, if this was 1, we'd be multiplying it by 1.08. We just have to keep changing this exponent. So in 5 years, it would look like this. 950 times 1.08 to the 5th. So now when I do it on the calculator, do this part first, not the multiplication. We want to do exponents first. Please excuse my dear Aunt Sally, the x comes first. 1.08 raised to the 5th. I get 1.469. I'll take that times 950, and I get 1395.8. There's probably not going to be 0.8 people, but it goes from 950 to 1395 at that rate of growth. How many students were there 2 years ago? Well, 2 years ago is back in time, and actually we're able to do time travel with this. But my exponent, instead of being 0, 1, or 2, it's 2 years behind that. So I'm going to put the -2 power. Anytime we're going back in time, we can do a negative exponent. So I'll just go 1.08 raised to the -2. Oops, I didn't type it right. Raised to the -2 power. And I got 0.857, take that times 950, and I'm getting 814.5. So there were less students 2 years ago than there are now with 950. Then this says, what multiplier would you have used if the number of students was decreasing by 8%? Well, remember when I said that the growth is amount above 1 or above 100%, so we did 1.08. If it's decreasing, that's 8% below 1. Let's just subtract. And 1 minus 0.08 would be 0.92. The b value would be 0.92. So I would have had my equation, if it said the population was dropping by 8%, I would write it like this. And that's how exponential functions work. Have a great day.